Okay, so I'm going to take you through the energy solution, or at least get you started for it. So if we look at what our givens are, we have the one roll that's just being dropped, and we have one that's being dropped and unrolled. So this one is dropped from big height H, little height. The speed that it hits the ground with, we're going to call V, and the speed that it hits the ground with over here, we're going to call that the velocity of the center of mass as it translates downward. And the time it takes to hit the ground is the same for both. So the energy approach sets the gravitational potential energy at the top equal to the total kinetic energy at the bottom. In case one over here, it's just going to be translational, so you're going to have a 1/2 mv squared on this side of the equation, and for this side of the equation you're going to have both the rotational plus the translational. And if we recall, the rotational kinetic energy is going to have that moment of inertia I. So if we choose it to be the moment of inertia about the center of mass, that's what we're going to, because we're looking at the velocity of the center of mass, so we want that moment of inertia to be through the center of mass. We can use the same one that we used for the steel washers that we used in the Conservation of Angular Momentum lab. And then you have your translational kinetic energy, which is going to involve a velocity of the center of mass squared. This one will have an angular velocity, but if we recall, the angular velocity is equal to the velocity of the center of mass divided by the radius of the rotating object. So again, and that'll be the outer radius of the piece of the toilet paper. So this one is a little bit challenging in that both sides, if we have our potential energy, which is going to give us our h over little h part, if we take the ratio of those, we're going to have v squared terms. So we need to use kinematics to get rid of the v squared terms and get them in terms of our known variables. So this v squared immediately is going to help lead us to think of using that the v squared equation from kinematics, where this delta x will be the different heights. The acceleration on this side would be the center of mass acceleration. On this side, the center acceleration is going to be little g, 9.8 meters per second squared. So that will help us get rid of the v squared terms, but we're still going to have that acceleration of the center of mass on this side. So if that's true, we still need to use another kinematic equation to get rid of that acceleration term. So remember, we know h, we know t is the same on both sides of the equation. So, and if we want an equation that doesn't have v in it, I'll let you kind of keep going with that. And you want acceleration in there, we can kind of come up with the last equation that we should use in order to solve this problem. So that's one way to do it. The other way to do it is, get my little thing here. So I've been using these at home too. There we go. And I think it might be actually even a more simple way to go about this. And it's the same idea, the one that you drop and the one that you unroll. Here we can set up a net force equation. What are the forces acting on it as it accelerates downward? And our acceleration is going to be equal to g because it's in free fall. This one, we would set up a net torque equation. And again, we'll have an expression that has the moment of inertia and the angular acceleration, and the angular acceleration is going to be equal to the acceleration of the center of mass divided by that outer radius again. But again, we have kind of the same kind of issue that we need to kind of get something with an h in it. And if we kind of recall, if we want to look at the heights, and we have things that have acceleration in it, and we also know that the time is the same for both, and we don't really care about the velocity, we can pick a kinematic equation that's going to help us set up this proportion. So I think this method has a little bit less algebra involved with it. Go ahead and give it a try, and again, reach out if you have any questions. I'm checking my email very frequently aside from my office hours.